This is part 2, the principle of least action. In part 1, we looked at 6 different physical systems. We looked at them using the Lagrangian, kinetic energy minus potential energy. The Lagrangian just perfect for Lagrange's equation, and we showed for each of those 6 different physical systems that Lagrange's equation gives us Newton's laws, which is exciting. But why? What's so special about Newton's laws? What is nature trying to do here? There's something philosophical perhaps about Newton's laws. You're trying to say that net force changes motion, mass resists changes in motion, but what is going on here? We're going to say action. Action is being minimized. This is the principle of least action. A natural system will behave in such a way as to minimize action. And what is action? Well, that equation gives you action, and I am stealing from Feynman's lectures, which are available on the internet, and they're just so pretty, especially these diagrams. Here we have a projectile. This is a position versus time diagram for a projectile. I was going to copy his diagrams and imitate them, but this is just, it's such an attractive diagram, I decided to steal it. And there it is. The principle of least action says action should be minimized. And again, this is a projectile in a way. This is something being thrown straight up and coming straight down. This is an x versus t graph. This is a position versus time graph. So we're not talking about two-dimensional motion here, just going straight up and straight down in a way that minimizes action. Let's make this a little bit more concrete with a specific example. We'll be using specific examples here. A ball is thrown straight upwards at 60 meters per second. Describe its motion during the first 8 seconds of flight, and we'll approximate g to 10 meters per second squared down. And there is our familiar equation for height, and then we'll plug in our values and we'll find the expression for velocity, and there we go. My contention is that this function for x and this function for x dot minimizes action. Let's see what we're talking about. There's our initial condition at t1. There's our final condition at t2. Just to show off, we can find the maximum height, which is kind of neat. And no, you say. What about this? What about this motion? Wouldn't this minimize the action? Isn't this a more economical way of getting from point 1 to point 2? Well, maybe it is. But you see, that guy is just not possible for a projectile on Earth. What you're talking about there, you're talking about a projectile that reaches a maximum height of 160 meters. Well, that's great. But in order to do that, you'd be shot off with about 57 meters per second. That's your initial velocity, and you're going to reach your maximum height in 5.7 seconds. We want to get to position 2 at time 2. You can't be there at 5.7 seconds like you would be if you were shot off with a smaller initial velocity. You got to be there at the right space and the right time, just like a touchdown pass in football. All right, let us plug in values for k and u. And there they are. Those should look familiar. Remember these guys, x and x dot. So we put them in, and we get to work. And we continue working, and continue working. We're trying to go as quick as possible here. If you want to fight through the weeds yourself, there's a PDF of the presentation available. And there it is. Our action, negative 6933 times the mass. That's the action for that path. And I tell you that that action is least. And I hope you believe me. Let's consider variations to the path. Again, thank you to Feynman. These are just beautiful diagrams. If you tried that second path that's kind of ducking underneath it and going above it, then what are you doing there? You'll have a bigger slope of your path. You'll have a bigger slope. You'll have a bigger velocity. You'll have a bigger K. You're going to have a bigger action. How about this path? The straight line path. That path from the initial condition to the final condition. What's the action for that path? Again, we'll plug in our initial conditions. Where are you at time 1? Where are you at time 2? And that expression for x and x dot, that would give you a straight line. Now notice that we're kind of ignoring the fact that x dot, the velocity, doesn't really work at the end points. But this is a made-up path anyway, so we'll just say that this made-up path, this made-up quote-unquote projectile, has some magic ability of having the right velocity at the endpoints. Don't worry, more hand waviness to follow. So we take our expression for the action, our k and our u, that's what it means to be a projectile. That's the k and that's the u for a projectile. Plug in our new x and our new x dot and do the work, and it's a little less work this time, and there it is. Our action for the second fake path, and notice that the action for that second fake path is more than the action for the original path. So far we have least action, at least the least action of those two potential paths. Here's another path. Here's another path, and there's a fun fact about this new path. If we use this equation for x and x dot, again, we meet the initial and the final conditions. Kinda, not so much with x dot, but definitely for x and t, we meet the conditions. Fun fact, we have a new max height. It's a higher max height this time. It's the same equation for k. It's the same equation for u. It's the same procedure, plugging in x and x dot, getting it in there, doing the work, continuing through, getting a value. By coincidence, it's the same value we had for that straight path, and there we go, and we're doing good. And I know what you're thinking. Okay, you showed that Newton's laws gave you the least out of those three potential paths, or those three possible paths, but are you really showing me that this is the line that has the absolute least action possible? And the answer is no. And the reason for that is because it's complicated. The principle of least action can be proved with something called the calculus of variations. Here's what we're doing. Take this expression for action and then give it a nudge. Give it a nudge, and you're trying to nudge the k and nudge the u, and we're trying to give it a nudge and show that it really is at the bottom. It really is a local minima. It really doesn't change when you give it a nudge. And you're thinking that that's easy. I've done differential calculus. That should be easy. You just take the derivative. But we're going to need this fancier way of doing it, the calculus of variations, because we're not just trying to find a variable where the value is the minimum. We're trying to find the function. We're trying to find not a value for x, but the function x and the function x dot that minimizes this action. Or consider a light bulb and then an observer underwater. How's the light going to get to the observer underwater? Will it take this path, or this path, or maybe this path? Which of these three paths? Well, we'll answer that with the principle of least action. But what's k and u? The energy of a light beam is just h times the frequency, Planck's constant times the frequency. So energy depends on the color of light, you could say. So that just, what does that leave us with the action? Oh, time. It means that the time will be minimum. Let's consider some values so that we have a practical example here that we can solve. And velocity is distance divided by time. So there we have it. Time is distance divided by velocity. And what about the velocity of light? We know the velocity of light, and we know that the velocity of light is smaller in water. There's the index of refraction, and you knew that was coming, so it's a little bit slower in water. How long will this light beam take to get from here to there with a straight line? Let's find out. Hey, look, a 3, 4, 5 triangle. Thank you, Pythagoras. And now we can find the time. It is about 39 nanoseconds, which is pretty quick. So don't blink. That's the amount of time it takes. So by minimizing action, we're minimizing time. So how long does this path take? Again, there are the values. There's Pythagoras. There is distance divided by velocity, giving us a time of 41 nanoseconds. 41 nanoseconds, which is a little bit longer than the first straight line path. So given these two paths, light prefers the straight line versus that wacky second path. But how about the path defined by Snell's law? This path, refraction towards the normal, Snell's law. There are the values. What is d? And what is 8 minus d? Well, we're asking Snell to give us the answer. The index of refraction, again, for water is 1.33. So go ahead, Snell, tell us the answer. And that requires a little bit of work, and a little bit of more work. I could evaluate that equation, but I'm too important, so I'll let a computer do it. And there we have d is equal to 2.59. That means 8 minus d is equal to 5.41. There are the values. Let's just make sure I did that right. You okay, Snell? Snell's okay. Good. Now, how long does that path take? The path defined there. Answer? 38 nanoseconds. 38 nanoseconds. That's even less than the straight line path, which means that light changes direction. It is refracted towards the normal in order to minimize time. Minimize time. And somebody's thinking, oh, this calculus of variation stuff, that sounds complicated, but I should be able to do this, right? I should be able to minimize time using differentiation. And yes, you can, and let's do it. And there's our expression for time. Time is equal to velocity divided by distance, so we're good. We'll tweak it just a little bit, and then take the derivative and set it equal to 0. Right? We took the derivative and set it equal to 0. This might require a little bit of meditation, because here we're using the function rule, which is just kind of like the power rule, but it's the function rule. What do I mean by a function rule? We'll consider that function. We have 9 plus d squared raised to the 1/2 power. That explains the 1/2. That explains the negative 1/2 power, and that explains the 2d, and that explains the other guy also, especially the 2 quantity 8 minus d times negative 1. Negative 1 is the derivative of d. It's like a function rule inside a function rule, but it's good. And there we go. And now this is more work, right? Yeah, that's more work. Good news. We've already done it. This is equivalent to a step that we had in the earlier derivation, earlier work. So we're good, and we're good, and we're good. And we have not just a small, but the least action. Snell's law gives you the least action that you could possibly have for light getting from here to there. Great. The least time, which is not exactly what we had with the projectiles. Kind of similar, but not exactly with the projectiles. Remember, all of these paths get to position 2 in 8 seconds. Each of these paths gets to that height of 160 meters in 8 seconds. So these paths all have the same time. They have the least action, though. The center path there, the true path, has the least action, just like the light path also has the least action. In the case of light, least action is least time. So there we have it. Projectiles and light beams united by action. One more to go, and that is the pendulum. Oh, you knew that was coming. We can't let the party end without doing some simple harmonic motion, because that means dancing with the trig functions, and the trig functions mean circle, but the circle also is a parabola. Did you know that a circle is the same as a parabola? Well, it's not, but it is when your x and y are small. Let me explain. There's our parabola equation. There's our circle equation. There's our circle equation again. If we are so bold as to let y squared approach 0 and get it out of the equation, if we allow that to happen at small x's, at small y's, where y squared is equal to 0, we get this expression for y. This expression for y, you could call it small thetas if you want to. There's our expression for y, which allows us to rewrite our potential energy of the pendulum. There's potential energy. We recognize him. There's the way we tweaked potential energy in part 1, but no thetas. We want x's. There's our new tweak to potential energy, which makes us happy because now the pendulum potential energy looks like the spring potential energy. They're both proportional to x squared. That's great. The connection goes even deeper if you remember omega. Omega, there it is. That means that potential energy for an object in simple harmonic motion is 1/2 m omega squared x squared, and that's where that equation came from. So let's use it in a practical example. We'll let L equal 1 meter. That's easy. Our displacement is 17 centimeters, so that means our angle is small. Okay. Our omega is knowable. Our period is 2 seconds. Fun fact, if you have a 1 meter long pendulum, the period is pretty much exactly 2 seconds. Fun fact there, but we're only doing the first half swing, so for us, T final will be at 1 second. There are our equations for x dot, and x double dot, and there they are with the information plugged in. Get out of here, x double dot. No one cares about acceleration and force and all that ridiculous stuff. Our initial and final conditions, and the path described by the real motion, the path described by Newton's laws, and described by the principle of least action, which we will show. And there it is, action, with a K and a U for the pendulum, which is different, looks different, is different than action for a projectile. That's the difference. And here we get to work, and we plug in the values, and we do the math, and we do more math. And hey, look, it's the double angle formula for cosine. That guy shows up at the strangest places, but we're done because we have action. Well, not exactly done, but we have action, and it's pretty small. You got to admit, that's a pretty small action there. How about we consider the straight line path? The straight line path from our initial to our final condition. That would mean a constant velocity. Imagine a world where the pendulum moved at a constant velocity. Well, the world would look like this. That's what x and x dot would look like. We'll plug that into our same expression for action. There they are. There they go. And here we go with a new calculation for action, which, as we knew would happen, is bigger than the action for that cosine function. That action for that cosine function, the real observed physics in the world, which is nice and which is different than projectile motion. So why, and again, these are position versus time graphs. Why does one look one way and the other look the other way? Well, the answer is one describes a pendulum and the other describes a projectile. Another way to say that, though, is that the U part of the action equation is different. They have the same K, but they have different U's, and that's what makes a pendulum, and a projectile in advanced classical mechanics. In classical mechanics, you worry about the forces. Here, we worry about the actions and the potential function, which is an improvement, and I'll tell you why. Because of light. If you're only worried about forces, if you can only think about forces, then you're going to ask a question like, well, what force causes that light ray to change direction? What force causes that acceleration, that change in the velocity, speed, and direction of that light ray? And there's not a great answer to that when you get down to the quantum level, when you're talking about things like light, but there is an answer with the action.